The SpaceX Starship is currently humanity's best hope for setting foot on the planet Mars in your lifetime. The feature that makes the Starship so well suited for this job is, of course, its incredible power. There's no doubt that a future Starship will have more than enough muscle to send both crews and massive amounts of supplies on their path towards Mars. Going up is one thing, but what about coming back down on the Martian surface? We are talking about the most complicated maneuver of the entire journey, the make or break moment, and there's a lot more involved in figuring it out than you might think. This is how the SpaceX Starship will land on Mars. Let's establish right now that we are not all rocket scientists or physicists. I'm definitely neither of those things, but luckily, we do not need to be geniuses to understand the basic principles behind interplanetary travel. So we're going to keep this all at a very accessible level. Before we can talk about landing on Mars, we need to know how the Starship got there in the first place. The thing that we always have to remember about space travel is that everything is always in motion, and within the context of a solar system, everything is moving in an orbit around the Sun. We are currently held in the gravity well of the Sun, and the only thing that prevents us from falling down any deeper is the orbital velocity of the Earth, which is approximately 30 kilometers per second. That's how fast we are traveling right now in a big circle around a star that takes 365 days to complete. Mars is further away from the Sun than the Earth, meaning that it isn't as far down into the gravity well as we are, and therefore Mars can travel at a slower orbital velocity without falling in. So Mars orbits the Sun at around 24 kilometers per second. Now, if we want to leave the Earth in a spaceship and explore the planets, we will become yet another object spinning around in the gravity well of the Sun. And just like the planet Earth, if we were to slow down our orbital velocity, we would start to fall into that gravity well. This will change our orbit in the direction of an inner planet like Venus. And by the same mechanics, if our spaceship starts moving faster than the planet Earth, we will rise up the gravity well, bringing our orbit towards an outer planet like Mars. So traveling through the solar system is all about changing your velocity relative to your starting point. The technical term that we use to describe this is delta V, where delta means change and V means velocity. We typically measure delta V in kilometers per second, so if the Earth is moving at 30 kilometers per second and you accelerate your spaceship to 31 kilometers per second, you have a delta V of 1. By the same measure, if you decelerate your spaceship relative to the Earth and travel at 29 kilometers per second, you also have a delta V of 1. And yet, if you blast off from the surface of the Earth at 1 kilometer per second, you are not going to begin rising up through the solar system. You aren't going to rise up above the Earth's surface because gravity and atmospheric drag are holding you down. These natural forces will affect the amount of delta V required to maneuver the spaceship. This is why it's so hard to get from the surface of the Earth to outer space. The delta V required to reach a typical low Earth orbit is going to be around 9.4 kilometers per second. That's a lot of acceleration, and that's why our Starship requires the massive power of the Super Heavy booster at launch. This is also why the Starship needs to stop for a refilling session in Earth orbit before it can continue on to Mars, because we're going to need a lot more delta V to complete this journey. In order to change velocity, we need propulsion, and propulsion needs fuel. The advantage of filling up in orbit is that it resets our starting point. From here, we only need another 9.5 kilometers per second of delta V to reach the surface of Mars, so basically equal to the change required just to escape the Earth's atmosphere. But there is going to be a big difference in the approach we take for the next leg of the journey, because while escaping the Earth was all about speeding up, landing on Mars is going to require a lot of slowing down, and this can be just as difficult to achieve. A fully fueled Starship in low Earth orbit is imagined to have enough thrust for somewhere between 6 and 7 kilometers per second of delta V. This obviously is a bit short of our 9.5 kilometers per second necessary to reach Mars, but that's okay, because the same forces that made it so difficult to escape Earth's atmosphere, gravity and aerodynamic drag, are going to work to our advantage when we come in for a landing, effectively increasing the delta V potential of our starship. So here's how it's going to go down. Okay, we are in orbit around the Earth, but even a few hundred kilometers above the surface, we are still firmly caught in the Earth's gravity well. The only thing keeping us up right now is velocity. If the starship were to slow down at all, it would start falling back towards the Earth. By that same reasoning, if we do the opposite and speed up, then we will continue to rise up into space. Because we are still so close to the Earth, we need a lot of delta V to fight against gravity. The ship will have to accelerate by 2.44 kilometers per second just to reach a height of geostationary orbit. Another 0.68 gets us to the height of the Moon. Up here, we are finally on the edge of the Earth's gravity well. The force of gravity is infinite, but the power of attraction dissipates relatively quickly as you move further away. Now, all we need is another 0.9 kilometers per second of velocity to escape the Earth's influence completely. From this point, floating in the vacuum of space far beyond the Moon, we only require 0.39 meters per second of delta V to achieve our Earth to Mars transfer velocity. This second leg of the journey has used up 3.6 kilometers per second of delta V, which is at least half of the potential energy in our starship, if not more, and that means that we do not have enough fuel left to successfully land on Mars with engines alone. And here comes the problem that we need to solve. All of the velocity that we acquired to escape Earth's atmosphere and gravity well has got us traveling around the Sun at a significantly higher speed than the planet Earth, which was already traveling at 30 kilometers per second to begin with. The planet Mars, on the other hand, is orbiting at a speed of just 24 kilometers per second. So we are moving significantly faster than our target planet, which means that we are going to overshoot the planet Mars and end up stuck somewhere in the asteroid belt unless we start slowing down. After several months of coasting through the vacuum of space, we need to execute our first deceleration burn. After flipping the starship around and getting the Raptor engines back up to speed, we have to shave off 0.67 kilometers per second of velocity in order to become captured in the gravity well of Mars. This is the first step in what's about to become a very rough ride. If we burn off another 0.34 kilometers per second of velocity, then we reach the height of the outer moon, Deimos. 0.4 kilometers per second of further delta V gets us down to the inner moon, Phobos. Here's where things get really tricky. By slowing down this much, we've already expended over 5 kilometers per second of the potential delta V in our fuel tanks, and that leaves us with somewhere between 1 and 2 remaining, but we need at least another 4.5 kilometers per second of delta V to safely reach the surface. In theory, this is still possible as long as we are very strategic about how we use our last bit of fuel, and it's important to remember that everything from here on out is purely speculative. This is our interpretation of the most logistically feasible Mars landing. If we want to conserve as much fuel as possible for our landing burn, then we need to take advantage of some external forces to slow our ship down to a reasonable velocity. Getting down into a circular low Mars orbit would use up most of our remaining fuel, so we probably shouldn't do that. In this case, we might be better served by inserting the ship into an elliptical orbit. So instead of flying in a circle, we're moving in an oval pattern with a low spot, or perigee, close to the planet and a high spot, or apogee, deeper out into space. By using this maneuver, we can start to take advantage of both aerodynamic drag and Mars gravity to help us slow down. The Mars atmosphere is still very thin, but we'll take any help that we can get. We can lower the perigee of our orbit down to the point where the ship actually dips into the upper atmosphere of the planet. By doing this very carefully, we can actually catch some atmospheric drag and lose a small amount of velocity before getting flung back out to our apogee, where, if we've done this properly, the gravity of Mars will pull us back in to repeat the process over again. Every time that we dip into the atmosphere, we gain a little more of that precious delta V, bringing us closer to the velocity we need for a soft touchdown on the planet's surface. But we can't keep this maneuver up indefinitely. Eventually, we need to transition from a shallow dip to a full-on dive through the Martian atmosphere. It's actually pretty difficult to achieve a landing trajectory for Mars because the planet is only around half the size of the Earth. That means the angle of attack necessary to get down below the sky is pretty steep. This means you need a lot of energy pushing the vehicle down in order to prevent it from skipping off and shooting back up into space. Again, we want to save our engines until the last possible moment, so that force to push the ship down deeper into the atmosphere needs to come from somewhere else. This is why the original SpaceX design for an interplanetary transport system in 2016 had an aerodynamic lifting body in the upper stage. Starship is much smaller than ITS, so it doesn't need as much aerodynamic force, but the methodology is still pretty much the same. On its final approach, Starship is actually going to flip over and come into the atmosphere upside down. So that's with the belly and tail pointed up and the nose pointed down. This way, the lift generated by the body is going to push the vehicle towards the surface on a steeper angle to achieve entry. We're also going to start losing a lot of velocity thanks to aerodynamic drag. Once the angle of attack is set, the Starship is going to flip around into the more traditional belly flop maneuver that we've seen on Earth. This is all about creating the maximum amount of drag that is physically possible and getting the velocity down, but this force can only accomplish so much. The maximum speed of a free fall is something that we call terminal velocity. Imagine you jump into a bottomless hole. Your body will accelerate as you fall up until a certain point when the drag and buoyancy of your body equalizes with the force of gravity and your speed becomes constant. One way that we cheat terminal velocity is by using a parachute. This greatly increases drag and slows down our terminal velocity. Starship isn't going to use parachutes, so there's going to come a point where the aerodynamic drag of the vehicle has done all that it's going to do and we reach terminal velocity. Due to the thinner atmosphere, terminal velocity on Mars is around 5 times faster than on Earth. In other words, that means you only get 1/5 the delta V accomplished by belly flopping through the air on Mars compared to what we've already seen Starship do on Earth, which means that it's going to require more engine power to land on Mars than it does on Earth. This is why fuel is such a major concern here. Assuming that everything up until this point has gone correctly, the Starship's engines will fire up one last time and flip the tail towards the surface, at which point the fuel in the rocket's header tanks will provide just enough delta V to bring our ship perfectly in sync with the surface of Mars, and we touch down softly. Now, that's a lot of stuff that has to go right, and there is zero margin for error. You either score 100% on the exam or you die. So by knowing all of that, we can appreciate that landing on Mars is going to be incredibly difficult in a massive vehicle like the Starship. It's much easier for NASA to land smaller and lighter vehicles on Mars because the potential delta V of your fuel is determined by the mass of the vehicle and the efficiency of the engine. So 1 pound of fuel accomplishes more change in velocity for a lighter ship than it does for a heavier ship, and there is a limit on the amount of fuel that we can bring to Mars. Starship would be much easier to land on Mars if it were lighter, but SpaceX needs it to be so gigantic to accomplish the goal that Elon Musk has set out, which is building a self-sustaining city of 1 million people on Mars. SpaceX is working hard on increasing the delta V of the Starship. They want to make Starship V2 longer with bigger fuel tanks, while also making it lighter at the same time and adding 3 more Raptor vacuum engines. The third version of the Raptor is currently in design and will probably offer higher efficiency and therefore more delta V potential. Now, there are other more long-term solutions as well. Remember Mars's outer moon Deimos? The delta V required to move from low Earth orbit to the orbit of Deimos is only around 5.3 kilometers per second. That's a lot more manageable, and imagine if you could build an outpost or a Mars gateway at the orbit of Deimos. Now we have the potential to refuel the ship so that it can make the hardest part of the journey with more than enough delta V to spare. This buys you a margin of error that would increase the safety of a Mars landing by orders of magnitude. So yes, landing a fully loaded Starship on Mars is going to be logistically insane. This is one of those situations where SpaceX won't know anything for certain until they try. We've seen this twice now with just launching the Starship, and both times it exploded in mid-air. Learning to land on Mars is more than likely going to be a similar affair. They are much more likely to fail before they succeed. They could fail multiple times. It's going to require a spectacular amount of willpower to make this work, to not give up, and probably more than a lot of people are genuinely prepared for. And then eventually, we try to do this with people on board, and calling this ambitious seems like an incredible understatement. But over the history of humanity, we've accomplished the impossible many times over. So, what's one more? Meet us back here every week for more updates on everything aerospace industry and interstellar exploration related. Make sure to give the video a thumbs up today if you liked it. That really helps us out for real. And subscribe to the Space Race for more videos just like this. We do one long-form essay and one news update every week. And if you'd like more, we've got 2 more on the screen for you right now.